Okay, so I am going to continue from where I left off, and so if you recall in the earlier discussion I had introduced a notion called the single particle or one particle Green's function. So, that involves something called a particle propagator, which could be something like this, or it could involve a whole propagator, which would, so this would correspond to a particle propagator, and this would correspond to a whole propagator. So, the point is that given the fact that these notions are somewhat unfamiliar to people who have not studied the subject, but those who have studied the subject will of course be familiar through their prerequisites. They would be familiar with the notion of the many particle wave function of the system. So, they would be more familiar with an object such as this, that so if you have n particles in your system, you know what this means. So, in the Schrodinger picture, this would be time dependent, and if you want to evolve this you know from a given time to a later time, this would be the solution of the time dependent Schrodinger equation. Okay. So, so people are going to be familiar with this, and this is somewhat unfamiliar, but it would be therefore desirable to link these two, you know, to be able to say how these notions are related to this notion. So, that is what I have been trying to do. So, in order to do this, so I am going to start with my one particle or the many body wave function. So, let us imagine I start like this. Okay. So, I have all the way up to R n, and then imagine that I decide to annihilate a particle, and this is going to basically mean, so let us imagine this is properly symmetrized to begin with, like I was saying. So, firstly this involves writing this. So, you have an n particle wave function whose Hamiltonian is described by h subscript n, signifying that it is the Hamiltonian of n particles, and then once you annihilate, the resulting state has one less particle. So, you should be evolving with respect to one fewer particle. Okay. So, that is going to be t dash there. So, that is what that is. So, this basically means that you are going to be doing this. So, it is going to be C r dash. So, then I am going to freeze the, because well, first I am going to evolve, and then I am going to freeze. So, I am going to freeze the last term there, and remember that when I annihilate, I pick up a square root of n, because you know the annihilation is basically square root of n times n minus 1. So, I am going to pick up a square root of n, and I am going to freeze the last variable. Okay. So, now I am going to call this entire thing, I am going to call this psi of whole parameterized by t dash, but acting. So, it is a parametric type of wave function, it is parameterized by t dash, but the interpretation is going to be that it is actually the wave function at time t equal to 0, but then it is parameterized by t dash, and it has one fewer variables than n. So, that means the number of dynamical variables is only n minus 1. So, what is the physical meaning? So, the action of the time evolved annihilation operator on the original many particle wave function is this beast here. So, the question is, how do I interpret this? So, the way I interpret this is that the whole wave function is one which has the property that if you evolve the whole wave function from t equal to 0 all the way up to t equal to t dash, you get a wave function which is the same as this wave function. So, this is the interpretation which makes it easier to understand what is going on. So, you just write it like this. So, this is going to be psi of r 1 r 2 r n minus 1 r dash t dash. So, we know what this is. See, what is this? This object is easy to understand what this is. So, basically it is just the time evolved version of well, it's firstly you time evolve this original wave function, then you annihilate a particle, that is what this is. So, you time evolve it and then you annihilate a particle. So, but the whole wave function is that wave function where you start off with one less particle to begin with, but it is already parameterized by t dash and r dash. Okay, so, there is some state parameterized by r dash and t dash, but it also describes a state with n minus 1 particles, but parameterized by r dash and t dash. That is your starting state, and you evolve that for a period of time called t dash until you reach a new state. And so, if that new state is called is exactly the same as this state, which is the the time evolved original state followed by annihilation. So, if these two are the same states, then you call this the whole wave function at parameterized by t dash. So, I understand that it is a little hard for you to grasp, because it is kind of, see, all I am trying to do is I am trying to translate what is really a complicated mathematical notion into ordinary English. So, that is likely to be quite ambiguous and probably unwise. But then this is how I would look at it if I wanted to interpret it using words. But then I will allow you to do it yourself whichever way you want. So, the equations are very transparent, they say whatever they want to say, and how you translate it into words is entirely up to you. So, the point is that having known what this whole wave function really means. So, let me go ahead and try to explain what this object is in terms of the wave function. So, namely I am going to explain what the whole propagator is. So, I am going to write down a formula for the whole propagator in terms of my many body wave function. So, that is something very desirable. So, in order to do this, so let me start off by defining my whole wave function, which is denoted by this g subscript less symbol. So, it is going to be denoted like this. So, now in terms of many body wave functions, clearly this is what this is. Well, a whole bunch of all the r's that are there times my many body wave function, which describes this state called S. I mean, this is the capital S, not that statistical parameter S. This is the state S. Okay. This is the uppercase S. So, R1 all the way up to Rn. So, this is what that is. I mean, this is the meaning of that. So, I am going to be able to write this in the following way. So, this also makes equally good sense, namely, you know, I am just explicitly writing this out. So, notice that I can always think of, you know, I can always write it like this. Okay. See, notice that I have just first I have taken the trouble to explain to you what this object, which is the annihilation of a particle with well defined statistics, of course, at a time t dash at position r dash is when it acts on given many body wave function. So, I have told you what that is. So, that is basically this object called the whole wave function parametrized by r dash and t dash. So, now, so as a result, this is nothing but, having known what that means. So, this is basically nothing but n, because there is a square root of n coming from this annihilation and another square root of n coming from this annihilation. So, the net result is a factor of n, and this remains as it is, and I am going to end up with this whole wave function parametrized now in this case by t and r. And like I told you, a whole wave function by definition has one fewer number of particles. So, the number of dynamical variables is n minus 1 rather than n. So, it is parametrized by this r and this t, because this r and t is the location at which you annihilate the particle. So, so, you can see now we have made sense out of the whole Green's function in terms of the many body wave function. So, it is basically what it does is, in essence, it is a kind of overlap between the many body wave functions. You find the overlap between two different many body wave functions, and you integrate over all variables except two of them, and you freeze those two variables to be the values at which you are going to create and annihilate. But then you have to also make sure that you properly evolve the state to the times that are required before you do this, before you evaluate the overlap integral. So, that is the reason why you should first make sense out of this object called the whole wave function parametrized by r dash and t dash before you interpret it this way. So, this is going to be your wave function description of the whole propagator. So, similarly, you can define the wave function description of the particle propagator. So, let me describe to you the particle wave function. To just cut a long story short, just like you have a whole wave function, you can have something called a particle wave function, again parametrized by t. But notice that unlike a whole wave function which has one fewer number of particles, a particle wave function has one more number of particles. So, that means that you start if your original system contains n particles, then you end up stopping not at n, but you add one more particle. Okay. So, that is going to be continue to be parametrized by r and t, and the meaning of this is basically you first evolve your original wave function up to time t, and then you add a particle which is the n plus 1th particle, because there are already n particles here. If you add one more particle, you are going to add it here at the location r, but then this state is no longer properly symmetrized, remember. So, what you should be doing is then go ahead and properly symmetrize. I mean, this is my statistical parameter S, which could be plus 1 if it is boson, or it could be minus 1 if it is fermion. Okay. So, now you are going to properly symmetrize this, and then you kind of do the anti evolution, because I told you that the interpretation is that you push this to this side and that gives you the interpretation. So, this wave function is that wave function which when evolved with this Hamiltonian for a period of time t becomes the same as this. So, that is the meaning of this particle wave function, just as it was in the case of the whole wave function. So, having defined the particle wave function in this fashion, so then you can go ahead and define the particle propagator, which is nothing but so you first create and then you annihilate. So, this is going to end up becoming this. Notice now that there are, because you have created, there are going to be one more number of particles. So, that the total number of particles n plus 1. So, you got to deal with that. So, this is parameterized by T dash, and it has one more particle and it has r dash, but then this continues to be at time t 0, because so we interpret this as the parametric dependence on time. So, the parametric dependence is now t in the other case, and this has just as before, it has one more particle and 0. So, this is the definition of the particle Green's function in terms of the many body wave function of the system, which presumably you are more familiar with, and in fact, most of us are more familiar with wave function, because that is how we learn quantum mechanics. We learn the Schrodinger's version of quantum mechanics, which talks about wave functions, and then when we have many particle system, like we start off by discussing helium atom and that sort of thing, and then we discuss wave function with 2 electrons and that sort of thing, and then we become familiar with wave functions with more than one particle, and that is very familiar to us. And so, when you encounter a completely new notion like the particle Green's function or the whole Green's function, then it is certainly very desirable to link it to some notions such as many body wave function, many particle wave function that you are already familiar with. So, that is precisely what we have accomplished now. Okay, so, the next topic, having understood what many body wave functions are. So, now that you know what it means, now you also know therefore why we are calculating it, because you see the whole point is that the wave function of a many body system contains a whole lot of information that we probably do not care about. It would be nice if we could write it down fully, but most of the time you can't. So, what you end up doing is instead define some object in terms of the many body wave function, but which contains far fewer variables. So, in this case precisely 2 vectors and 2 numbers like t and t dash. So, even though the many body wave function contains a huge number of variables such as r1, r2 up to rn. So, in this definition you basically integrate over all of them. So, whatever remains is just 2 or 3 like that. So, the implication therefore is that it is going to be, so you will have to develop techniques where it is far easier to evaluate such an object then it would be to evaluate the entire wave function. So that is the claim and that is the implication. So, in order to verify this claim or make that convincing, that claim convincing, I will have to first rewrite my Hamiltonian also in terms of these creation and annihilation operators. Because remember that we took the trouble to explain that these operators obey these types of commutation, equal time commutation rules. So, they obey this equal time commutation rules. Okay. So, now the point is that now these operators they do things amongst themselves. So, we know how they commute or do not amongst each other, we know exactly how the algebra amongst themselves. So, it is nice to now go ahead and start expressing every other operator we are familiar with in terms of these creation and annihilation operators. Then we will be able to study all these many body systems purely in terms of these operators. So, as opposed to, for example, position and momentum that you kind of grew up with. So, let me start with that Hamiltonian that you grew up with, namely this. So, so you grew up with this sort of Hamiltonian, which is describes the two body wave function. Okay. I mean, typically it only depends on the distance between two objects. So, I am going to start with this, the simple n body system with two body mutual interactions between the particles. So, now the claim is that this is exactly the same as this object. So, I am going to claim that this object is the same as So, I am going to claim that it is exactly this. See, one advantage, okay, first let me write it down, and so it is going to be this. So, this is the same V there, this is the same V as before. Okay, this is fine. So, this is the claim is that these two are identical. So, these two are identical, they are the same operators. So, now let us stare at both and see what are the advantages and disadvantages of doing this. See, firstly this really means minus h bar squared del squared. I mean, this is this operator del r, del with respect to r. Okay. All right. So, what is the advantage of doing this? Firstly, here you see that this really does contain capital N number of variables. So, if I wanted to solve Schrodinger equation, this would really be this. So, I would be solving this E psi. But then stare at this, you will see that instead of containing n variables, it is just I mean I am just making do with just one r and at most two of these r's here. So, it seems miraculous that as original Hamiltonian, which contained n variables, has now completely transformed to another operator, which we are claiming is identical to the earlier one, but nevertheless contains only two variables integrated over and so on. So, of course, that is an illusion, because the definition of C and C dagger is involves these many body wave function, which actually contains information about the number of particles in your system. So, So, it contains the information about how many particles there are. So, that is implicit in the definition of C and C dagger. So, now how do I go about proving that these two are equal? So, so the easiest, I mean the only way actually is to just show that the action of H, I am going to call this H star maybe. Finally, I am going to show that H star is identical to H. So, the claim is that see, I have to show that H star acting on some wave function, not just wave, on anything, not just I am not talking about this as the eigenstate of H or anything, it can be anything which is properly symmetrized. So, any function of n variables that has a proper permutation symmetry. So, the claim is that this H star acting on such a wave function is the same as H acting on that wave function. So, if I can show that for every Fs, then I can show that this claim that these two operators are the same is convincing. So, so in order to do this, so of course, I am not going to do this in full rigor. So, I am going to use a plausibility argument, but I am going to start with a simple function of two particles which has the proper symmetry. So, now I am going to ask myself what is this? Okay. So, what is this? This is going to be clearly this. Okay, so that is what that is. So, now let us see if we can simplify this further. So, notice that this acting on psi of r, it just annihilates a particle. So, I can just go ahead and rewrite this as psi of r 1 comma r with a square root of 2, because there are two particles to begin with, and then I annihilated it. Okay. Now, I have to first do this is minus h bar squared del squared. So, then having done that, I have to create a particle at location r. Okay. So, this is one particle. So, I have to create one more particle at location r. But then keep in mind that once I create one more particle, I am going to have two particles in my system, and then I have to take care to properly symmetrize that. The implication is that it comes properly symmetrized. So, I have to leave it properly symmetrized, the way that our teachers are expected to leave the blackboard clean when we exit the classroom, because it was clean when we entered. So, that is how it works even here. So, if it is properly symmetrized when it was given to you, you should leave it properly symmetrized when you are done with it. So, how does that work? So, basically when you create, so you are going to create by adding a particle again at location r, but then you have properly symmetrized that. Okay. So, when I do that, I end up well, so this first term, I am talking only about the first term. So, the first term is going to look like this. So, I am going to add a particle at r 2. Well, this is always there, but then there is this which has been frozen here, and there is the S symmetry. So, I have to flip the R1s and R2s and put an S factor, this small s, which can be plus 1 or minus 1, psi s R2 R. Okay. So, this is going to be clearly because of the delta functions, it is going to become minus h bar squared over 2 m delta 1 squared minus h bar squared over 2 m delta 2 squared of psi s r 1 r 2. So, that is the first term. So, that is plus second term which I have not done, that is the second term is this one. So, I will come to the second term later. Okay, so the only the first term is just this. So, you can see that that is same as this. So, this is just the kinetic energy of the first particle plus kinetic energy of the second particle, which should be corresponding to this. So, if there are only two particles, so it's so we have convinced ourselves that this second quantized form of the kinetic energy is exactly what we would get if we had explicitly listed all the particles in terms of position and momentum p squared. So, now let us come to the second term, which is the potential energy of the system. So, this potential energy is going to look like this. So, the potential energy operator, I am going to act on that two particle wave function and see what comes out. So, when you take a wave function and you operate it on a wave function with two particles. So, I am just going to write a sequence of steps which you can I am sure understand what I am doing. There is going to be a square root of 2 because once you annihilate. So, you notice that first you are going to annihilate a particle. So, it is going to end up looking like this. Okay, so you are going to annihilate two particles. So, I am going to do that in one shot, because once you annihilate you end up with a wave function of just one particle, and if you have a wave function with one particle, annihilating one more is a trivial activity, and I am going to do this in one shot instead of making two steps for it. Now, I have to start adding particles. So, annihilating is easy because all it means is freezing the variables to whatever it is, wherever it is you want to annihilate. But then adding a particle involves adding a new dynamical variable and then properly antisymmetrizing or symmetrizing. So, let us do that. So, if I do that, I am going to skip some steps and I am going to allow you to think about it. So, if I add one more, when there are no particles to begin with, adding is easy, it is just a delta function. But then having added this, so this is going to go away and it is going to become r dash minus r 1. So, that is what it is going to become. But then now I have to add one more. So, if I add one more, so it is going to be square root of 1 plus 1, because this is a state with one particle and I add one more. So, creation gives me square root of 1 plus 1. So, that is another factor of square root of 2 that gets multiplied with this square root of 2, which cancels with this 1/2, and then I end up with this result. Okay, I end up with this result because of the requirement of properly symmetrizing. I end up doing this. So, that is what that is. So, you see that this is precisely what you would expect from here. So, if you have two particles, if it's just R 1 and R 2, I is not j. So, it's either 1 and 2 or 2 and 1. So, you add them up and then they are the same thing. So, that gets cancelled out here. So, if you have the potential energy of two particles, you just take I equals 1, I is not equal to j, and I can be either 1 or 2. So, either I is 1 and j is 2, or I is 2 and j is 1. So, for both these the answer is the same. So, when you add them up, that cancels with this 2 here, and you get V of R 1 minus R 2, which is precisely this times the wave function that you acted this operator on. So, you can see that we have now convinced ourselves that this operator is same as sigma I equals 1 to n p I squared by 2 m, and this operator, this whole operator is nothing but this one right there. So, it is just the potential energy of the system. So, in the next class I am going to explain how to write down the density operator, which is defined like this. So, this is the local density of particles at location I, or the current density. You could describe something called the current density, which is basically the velocity of the particle, which is momentum divided by mass. But then notice that in quantum mechanics, P and R do not commute. So, what you should be doing is rendering it Hermitian by taking a symmetric combination and taking the average of the symmetric combination. So, this would be the current density. So, this would be called the current density, and this is the particle density, or just density, particle density. So, this is the particle density of the system, and this is the current density at location R. So, just like we did here, so we expressed the conventional description of the kinetic energy and the conventional description of the potential energy in terms of the second quantized or the creation annihilation description. So, we would like to express the density which is expressed using the traditional variables R 1, R 2 up to R n, also in terms of creation and annihilation operators, and similarly the current density, which is expressed in terms of the conventional variables, which are R 1, R 2 up to R n and P 1, P 2 up to P n, also in terms of creation and annihilation operators. So, that is what I am going to do in the next class. I hope you will join me for that. Thanks.